Okay, this is 2018, numbers 26 through 30. 26 is B, 27 is A, 28 is C, 29 is E, 30 is D. As always, just watch the ones you need to. So, 26. So they're looking at 3% or no more than 3% being underweight. They did a sample and they found 40 packages out of the 1,000. So that's like our p hat, right? If we're looking at the proportion that are underweight, 40 out of 1,000. And they wanted to know, is this enough evidence for us to say that's more than 3%? So if you think about their hypotheses, the null is that the proportion underweight is equal to 3%. And the alternative is that the proportion underweight is greater than 3%. So they want to use this sample to determine that. Now, the sample they did get 4%, but just because that's from a sample, is that different enough from 3% for us to say confidently that yes, of all of the packages, not just of that sample. Okay, so these are all based off of p-value here, or that would eliminate A, right? Just because the sample is 4% doesn't mean all of them are 4%. So the rest of them rely on a p-value, which is what we want to look at. So this is a one sample z-test for proportion. So I'm going to go ahead and find that test, or one prop z-test. Okay, so we're looking at 3%. That's what we're comparing to. And there were 40 out of the 1,000. And my HA had greater than. So we run that test. Okay, we see our p-value is 0.0318. Okay, so we can automatically eliminate these two. Okay, so does this mean yes or no? So our p-value is less than our alpha level. That means we would be able to reject HO and we would be able to conclude, or we have evidence that it is greater than. So we would say yes, because we'd be able to reject. Okay, next one is talking about a sampling distribution for a sample mean. So that's, my sample mean, I'd be looking at like mu of x bar, sigma of x bar, and so on. So we know that sigma of x bar is equal to sigma over the square root of n, which means as n gets bigger and bigger, the standard deviation of the sample means gets smaller and smaller. So the bigger n, the less variety I have, the more accurate my x bar is going to be. So which of the following, we're ordering from the smallest n to the biggest n. So what I'm going to look at is standard deviation. So for the least value of n, I would need the biggest spread. So A definitely has the biggest spread, right? The biggest range there, biggest variety in values. The next biggest spread would be C, and the smallest spread would be B. So that matches up with A. Okay, looking at 28 then. So a key to look at here is we're looking at adult volunteers. So that's not necessarily a bad thing. Sometimes we really can't avoid using volunteers, but that kind of limits the scope of our results. So because they looked at volunteers, I couldn't really generalize to all adults, but I could to adults that are similar to those in the study. So if I had a random sample of adults, I could generalize to all adults. Since I use volunteers, I kind of got to keep it similar to who I used. So it doesn't necessarily mean that we don't have any sort of evidence. It's just only applies to people that are similar to those in the study. So that's matches up with C here. So it can't be all people who consume soft drinks. It can't be all adults. C is is the most correct answer there. Okay, looking at 29 then. So they want us to come up with a 95% confidence interval, who are somewhat supportive or very supportive. So we're looking at this chunk here. So this is a total of 723 out of the 1,018 people that they asked. So this would be our p hat. Okay, so to make a confidence interval out of that. Now, they do have it broken up, the formula broken up here, but I think it's still easier to run the confidence interval in the calculator and kind of go from there as opposed to trying to figure out the formula. So for reference, this is equal to 0.71 when you divide those. So A and B are already out. We just need to figure out what the margin of error is. So when I go to the calculator, I'm going to do a 1 prop z int. There it is. Okay, so there were 723 out of 1,018. And they said 95% confidence interval. All right, so go ahead and calculate here. So we see our interval. So what we want to pay attention to is these, right? So we need to know the margin of error. So the margin of error would be from 0.71 to 0.738018, or from 0.68235 to 0.71. So either of those distances, they have to be the same, would give us that margin of error. So when I look from 0.71 to 0.738, right, that's about 2% difference, or closer to a 3% difference. So I know it has to be E then. If you wanted to do it exactly, you could do 0.73808 minus 0.71, that middle value, and you can see exactly there as well. So this is the one that fits. Okay, last one for this set then. So they're claiming that 400 is the number of recharges, recharge cycles, and they want to know how the central limit theorem applies. So in general, the central limit theorem tells us about the distribution of x bar, the sampling distribution of x bar. It does not tell us anything about the original population. So imagine I've got this giant pile of batteries and I'm looking at 100 at a time. So I'm going to select 100, find their average, put them back in. Select another 100, find their average, put them back in. Another 100, and so on. So the central limit theorem doesn't tell me anything about the entire population or that original bucket. It only tells me what happens when I take a set of 100. Okay. So the distribution of the number of recharge cycles is approximately normal. I can't say that. Okay. I can't say this is saying the same thing. This is saying the same thing. It only tells me about the distribution of the sample means. When I put all of those x bars together, what will it look like? And it will be approximately normal based off of the sample size, right? I always have to have the sample size or n being greater than 30. So this one matches. It has nothing to do with the population mean at all. It only has to do with the sample size.